In this video, we're going to have a bit of fun and talk about some special relativity, namely the Lorentz Boost, and we're going to make use of the split complex numbers. And what I'm going to show you is that in one direction, the Lorentz Boost can be written in a very compact equation, which is going to be ct, which is going to be the speed of light times time, plus x, which is a spatial coordinate, times j, which is the split complex unit, multiplied on the left by e to the minus phi j, where phi is the inverse hyperbolic tangent of v over c, is equal to the boosted coordinates. Now, special relativity is one of the big intellectual accomplishments of physics, so I can't possibly do the whole topic justice in one video, but let me attempt to outline the basic ideas here, and further relate them to Galilean relativity, which is our naive view of relativity. So let's say we have two people, A and B. They both have different coordinate systems. A is going to measure his coordinates as tx, where t is time, x is space. And then B has got his coordinates, which are going to be t prime, x prime. So I might refer to these coordinates as the primed coordinates, or the boosted coordinates. And further suppose that B is moving relative to A with a velocity of v to the right. Now, there's a way to convert these coordinates one from the other. And if we use our naive view of Galilean relativity, the way to convert t prime to t is that they're just equal. And the way to convert x to x prime is as follows. You take x prime, and that's going to be equal to x minus v times t, where remember v is that velocity that b moves relative to a. So this is the coordinates transformation, called the Galilean transformation, which is the incorrect notion of relativity. So conceptually, what you've got going on here with these pair of equations is just a coordinate transformation from A's coordinates, tx, to B's coordinates, which are t prime, x prime. So you give me some coordinates in A's frame of reference, I tell you what the B coordinates are going to be. And furthermore, this transformation is called a linear transformation. And since it's a linear transformation, it has a matrix representation. So I can also write the vector t prime, x prime is equal to the matrix 1, 0, minus v1 times the vector tx. And this matrix equation, or matrix vector equation, is equal to this pair of equations here. Now, one of the big intellectual accomplishments in physics is to recognize that that whole coordinate transformation that I just told you about is actually incorrect. And to see why it's incorrect, let's consider the modified thought experiment, that B moves with a velocity of 1/2 the speed of light. And the speed of light is 3 times 10 to the 8 meters per second, so this is going to be 1.5 times 10 to the 8 meters per second. And let's suppose that A shines a light to the right. So that light is going to move with a velocity of c, or 3 times 10 to the 8 meters per second, and that light and B are going to move in the same direction. So now you ask, what speed is B going to measure this light moving at? Now, if you take the whole naive view, you would say, okay, well, the speed of light is c in this direction, and this guy is moving half the speed of light, so he's going to perceive it as a little bit slower. And how much slower, or what speed he's going to measure? Well, he's going to measure c minus c over 2, or he's going to measure 1.5 times 10 to the 8th meters per second as the speed at which that light is moving. Now, that's incorrect. He would actually measure it as c still. So that's one of the big conceptual defects in the Galilean transformation, is that you would predict different people, depending on the velocity that they're moving, to measure the speed of light differently. In this case, we would predict B to measure the speed of light is moving slower than A. And you can always conjure up different thought experiments. So if you make B move to the left, he should measure the speed of light is going faster. So we know that this is the big conceptual defect, and the coordinate transformation that we need to move from tx to t prime x prime has to preserve the speed of light. And furthermore, the speed of light has got to be preserved no matter the value of v. So physicists thought long and hard about this, and they came up with a coordinate transformation. And unfortunately, I'm not going to derive it for you from scratch, but let me just tell you what it is. So the t prime is going to be gamma, which I'll tell you what that is in a second. It's going to be gamma times t, the unprimed t, minus v over c squared times x, which is the unprimed space coordinate. So that's the transformation you're going to need to calculate t prime. And now the second equation, x prime, is going to be gamma times x minus vt. So pretty simple. And that gamma is a dimensionless number which is calculated from the following formula: 1 over the square root of 1 minus v squared over c squared. And this thing is called the Lorentz factor. Now when v is equal to 0, gamma is going to be equal to 1, and as v increases, gamma goes up toward infinity. So if this is kind of new for you, you can just conceptually think of this as being some linear transformation from tx, the tx coordinates, to the t prime x prime coordinates, just like the Galilean transformation. In this case, the coefficients in front of t and x are going to be different. For example, the coefficient in front of t here is going to be gamma. The coefficient from x is going to be negative gamma times v over c squared. And you get 2 more coefficients down there. But conceptually, it's just a linear transformation from tx to t prime x prime. Now, what we're going to begin doing is rearranging the furniture of those 2 equations that I just showed you before. And those are called the Lorentz Boost, by the way. And what I'm going to do is I'm going to start to involve hyperbolic trig functions. Now, what I'm going to do is I'm going to start with the analog of the Pythagorean identity for the hyperbolic trig functions, which is cosh squared of phi minus sinh squared of phi is equal to 1. And phi is going to be some hyperbolic angle, but you can still think of it as an angle. But no matter what I plug in, this identity is still true. Now what I'm going to do is I'm going to divide both sides by cosh squared of phi. And this is something you would probably see for the trig identities too, for normal circular functions. So when I do that, I divide cosh by cosh, I get 1 minus, then here I get sinh squared over cosh squared, which in the hyperbolic functions that's called tangent, or the hyperbolic tangent squared of phi. So that's why I get on the left-hand side. And on the right-hand side, you could write this as the hyperbolic secant, since it's 1 over a cosine, but I'm just going to leave it alone as cosh squared of phi. And next what I'm going to do is I'm going to invert both sides. I'm going to take the reciprocal to solve for cosh squared of phi. So what I could say is that cosh squared of phi is equal to 1 over 1 minus tangent squared of phi. And finally, I'm going to take the square root of both sides just to solve for cosh of phi. And what I get is 1 over the square root of 1 minus tangent squared of phi. What's neat about writing cosh phi in this way is that it looks pretty similar to that Lorentz factor gamma that I mentioned before, in that it's 1 over the square root of 1 minus something squared. In the case of gamma, it's v over c, that's the thing being squared. In this case, it's just tangent of phi. Now, the insight is, well, why not I just make tangent of phi be equal to v over c? In that case, I just make the substitution, and what I get, just plugging in for tangent of phi, is I get 1 over the square root of 1 minus v squared over c squared, being exactly equal to cosh of phi. That's again equal to gamma. So by that substitution, or I guess I should say that assumption that tangent phi is equal to v over c, I get the additional relation that cosh of phi, whatever this phi is equal to gamma. So now I've got the relation between this hyperbolic angle phi and the v's and c's and the gammas. Now the one hyperbolic function that's left out is sinh of phi, but I can derive what that is quite easily. And what I'm going to do is I'm just going to recall that tangent of phi is equal to sinh of phi divided by cosh of phi. And just solving for sinh, I get that sinh of phi is equal to cosh of phi times tangent of phi. And I know what these two are already. So sinh of phi is simply the product of these two. So it's going to be gamma times v over c. So these are the nice relations I can get between the hyperbolic trig functions of this hyperbolic angle and the v's, c's, and gammas. And if you're wondering, well, what the hell is this hyperbolic angle? I'm just going to turn around and say that phi is equal to the inverse hyperbolic tangent of v divided by c. Just taking this equation and solving for phi. With those identities in hand, let's start rearranging the furniture for this Lorentz boost. The first thing I'm going to do is I'm going to distribute the gamma. So I'm going to get that this equation is equal to gamma times t minus v over c squared times gamma times x. And I'll also distribute this gamma here too. So I get gamma x minus gamma v times t. And what I'm going to do for this first equation is I'm going to multiply both sides by c. So on the left, I'm going to have c times t prime. And I'm going to multiply by this by c as well. So I'm going to get that gamma times ct. I'm just going to put that in parentheses for emphasis. Minus v over just c, because one of those c's is going to cancel, times gamma times x. So that's my modified equation here. And what I'm going to do here for the new x prime equation, I'm going to try to line up the t's in a column and the x's in the column because I'm going to eventually write this as a matrix. So I'm going to write this first term first, this minus gamma v times t. So I'm going to have minus gamma v. Now instead of writing t, I'm going to actually write this as ct divided by c. Now you see I haven't changed anything because I could always cancel out the c's and recover this term. But I wrote it as ct because I have a ct up there as well. And it's going to make the coefficients come out pretty nice. And then I'll write the second term second, plus gamma times x. Now what I'm going to do now is I'm going to write this ct prime x prime as a vector. And I'm going to write this pair of equations as a matrix times a vector. And the input vector is going to be ct and x. Now what I do is I just read off the coefficients. The coefficient for ct is just gamma. The coefficient in front of x is minus v over c times gamma. Now the coefficient here in front of ct is actually the same one here, minus v over c times gamma. And the final coefficient there is just gamma. So you see I was able to write the two equations for the Lorentz boost as a matrix times a vector, giving a new vector. And the coefficient matrix was as follows. But the reason I did this whole thing is to relate it back to these trig identities, or these hyperbolic trig functions. Now what I notice is that these coefficients are precisely the ones I was deriving here. So I can rewrite this. I would just keep the vector there, ct prime x prime is equal to, now what was gamma equal to? That was cosh of phi. So I'm going to write cosh of phi. What's this one? The minus gamma times v over c. That's minus sinh of phi. It's the same thing down here. So again, minus sinh of phi. And again, I get a gamma here too, so that's also cosh of phi. And that's still times the input vector, which was ct x. And I should also point out too that multiplying by c, this isn't something really foreign to people working in physics. They often draw their time diagrams as not t's, but c times t. Nonetheless, at this point, all we've done is really rearrange the furniture. We haven't really added any concepts here yet. But the big concept here comes from the recognition of the form of this matrix. I see that the diagonals have the same entry, and the entry down here is precisely the same as the one up here. So I could say that the abstract form of this matrix is AB, BA, where I have the same entry down a diagonal, and I have the same entry on the anti-diagonal. Now, such a matrix is actually the matrix representation for a split complex number. And if you haven't heard of that, I encourage you to check out some of my other videos, especially the previous one where I go over the matrix representation of the split complex numbers. And the way to convert such a matrix of this form back to a number of the form a plus bj is just to read off the coefficients in the matrix here, the entries in the matrix here. So I claim that this matrix actually represents the split complex number cosh of phi minus sinh phi times j. And this whole matrix equation can be reinterpreted as that split complex number times ct plus xj is equal to the new split complex number ct prime plus x prime times j. So this whole thing, this whole Lorentz boost, can be rewritten as an equation about split complex numbers. That's the big insight. And again, if you haven't heard of these split complex numbers, I encourage you to check out my videos. But the down and dirty way of thinking of it is you multiply out these numbers just like the complex numbers, except when you get a j squared, replace that by with a plus 1 instead of a minus 1. And multiplication just works as you normally would expect. And hopefully you can see that if you just do this multiplication and set both sides equal to one another, set the real part and the imaginary parts equal, then you get the Lorentz boost. Now there's actually a very neat way in which we can write this equation, and it has to do with this very special split complex number that we're getting out here, this cosh of phi minus sinh of phi times j. Now if we go back to the complex numbers, we have Euler's formula, which says that e to the theta I is equal to cosine theta plus sine theta times I. Now it turns out in these split complex numbers, if I have e to the theta times j, there's actually an analog to Euler's formula which says that this whole thing is equal to cosh of theta plus sinh of theta times j. Now with that insight, I can rewrite this split complex number here as e to the minus phi times j. Now why is that? Where does the minus sign work out? Well, cosh, like cosine, is an even function, so cosh of phi is actually equal to cosh of minus phi as well. And similarly, sinh, like sine, is an odd function, which means that minus sign can actually move in front right there. So this whole thing is just equal to e to the minus phi times j, just using this formula here. And again, I'm just asserting it in this video, but I've got the details in some of my other videos. So I'm going to rewrite this split complex number as e to the minus phi times j. I'm going to leave this one alone as ct minus x times j. And that's equal to this one over here, which is the boosted coordinate. As in the complex numbers, I could change up the notation a little. And what I'm going to do is I'm going to write these split complex numbers as ordered pairs. So instead of, let's say, ct plus x times j, I'm just going to write ctx, where the first component represents the real part and the second component represents the imaginary part, or the j part. So I just rewrite this using that order pair notation. But I write in this way just to be a little bit suggestive. What I have here is some ordered pair being operated upon on the left by e to the minus phi, which remember this is some hyperbolic angle, times j. And this is very suggestive because in the complex numbers, let's say we have some complex number, z1, if I multiply on the left by an exponential of some angle theta times I to get a new complex number, z2, what this is a rotation of z1 to z2 by some angle theta. And this turns out to be in the counterclockwise direction if theta is positive. Now, a similar sort of thing is very much true in the split complex numbers. Because see here, I have an exponential of some hyperbolic angle instead of a circular angle here. So what this really represents, this multiplication by an exponential, is a hyperbolic rotation. And again, this is nothing new. This is a common concept in relativity, that when you think of time and space as being united like this mathematically, this ctx, when it gets transformed to ct prime x prime, this primed coordinates represents a hyperbolically rotated version of these input coordinates. So this whole business about hyperbolic rotation is really the main reason why I made this video, so I can show you how this equation can be written in this form, where the input coordinates get operated upon by an exponential of some angle times j to give the outputs, and that represents a hyperbolic rotation. So that's pretty neat. Another thing that's very important to put out too is that suppose instead of going from the unprimed coordinates to the primed, I want to go in the reverse direction. Suppose I had the primed coordinates, I want to go back to the unprimed coordinates. So I'm asking, what is the inverse Lorentz boost? Now, when you're thinking of exponentials like this, what I'm asking is just solve for ctx. And when you work with exponentials, it's totally obvious what this is. So what you're going to do is you're going to multiply both sides by e to the positive phi times j times ct prime x prime is equal to e to the positive phi j times e to the minus phi j times ctx. And it turns out you can work with exponentials in the way you would expect, that the arguments add like this when they're being multiplied. So I actually get e to the 0 up there in the argument, which is of course equal to 1. So I just get ctx. And on the right hand side, I have e to the positive phi j times ct prime x prime. So you see that the angle being used to rotate from the unprimed to the primed is minus phi. To rotate from the primed to the unprimed is the positive phi. Another neat thing you can do with these exponentials of split complex numbers is velocity addition, which is another important concept in relativity. So let me outline a little thought experiment. So A, we have three people. This time we have A, B, and C. A is going to be stationary. His coordinates are going to be CTX. B's coordinates are going to be CT prime X prime. And C's coordinates are going to be CT double prime X double prime. Now, what's going on here is that B is going to move with a velocity of v1 relative to A. So this is v1 relative to A. Now, the new part here is going to be that C relative to B moves with a velocity of v2. That's going to be relative to B. Now, the question is, how quickly is C moving relative to A? And let me call that one v3. So this is the velocity addition question that we're asking here. And there's a well-known formula to do this, but let's derive it now. So let me first transform these coordinates to these coordinates, and we have the formula for that. That's CTX. That's going to be operated upon by an exponential of e to the minus phi 1. I'm going to call this phi 1 now. What is phi 1? That's going to be the inverse hyperbolic tangent of v1 divided by c. And that's going to boost to the primed coordinates, CT prime, X prime. And now I have a similar equation when I boost the B coordinates to the C coordinates, or the prime coordinates to the double prime coordinates. And that equation is going to be pretty similar. It's going to be CT prime, X prime, multiplied on the left by e to the minus phi 2 times j. And phi 2, you might guess, is the inverse hyperbolic tangent of v2 over c. And that's going to give me the double primed coordinates, which is going to be CT double prime, X double prime. Now what I could do is I can boost the unprimed coordinates to the double prime coordinates all in one step by just composing these two equations. So I have CTX. Now if I just take this primed stuff here, these prime coordinates, and substitute it right there, I can see that I'll have CTX being first multiplied by e to the minus phi 1 times j, then secondly by e to the minus phi 2 times j, is equal to the double prime coordinates. Here I've moved all the equations to the top, and the phis are to the side here. So here I have two exponentials multiplying one another, and I could do what you would normally expect to be able to do with exponentials. I could just combine them all into one. So I just add the arguments, and I get e to the minus the sum of phi 1 plus phi 2 all times j times CTX gives me the double prime coordinates. So I see that the unprimed can be boosted to the double prime coordinates by some hyperbolic angle, which is phi 1 plus phi 2. Now let me give that a name. Let me call it phi 3. And this phi 3 is actually going to be related to the velocity of v3. That's going to be the sum of phi 1 plus phi 2. So this equation is pretty interesting too, because it means that you can add the hyperbolic angles when you're interested in adding velocities. You can't necessarily add the velocities, but you can add these hyperbolic angles together. Now, what's phi 3 going to be? Well, that's going to be the inverse hyperbolic tangent of v3 divided by c, and I'll leave the right hand side alone, just phi 1 plus phi 2. So v3 is that thing I'm interested in, so let me try to solve for that. And to do that, I'm going to take the hyperbolic tangent of both sides, and what I'll get is v3 over c is equal to tanh of phi 1 plus phi 2. So this is what I have so far, that v3 over c is equal to tanh of phi 1 plus phi 2. Now it turns out that just like in normal trigonometry for the tangent function, there's an addition formula for hyperbolic tangent. And it's actually very similar to the normal tangent function. So let me remind you what that is. If I have just plain old tangent of, let's say, a plus b, this can be broken apart like this. The numerator is going to be tangent of a plus tangent of b, and the denominator is going to be 1 minus the product, tangent a times tangent b. Now the formula for hyperbolic tangent is exactly the same, except this minus sign becomes a plus sign. So that's another quite remarkable thing about these hyperbolic tangents, or hyperbolic trig functions, that they're quite similar to the normal trig functions in many ways. So I'm going to break this thing up. So I'm going to write the left-hand side, v3 over c is equal to tanh of phi1 plus tanh of phi2 as a numerator. And the denominator is going to be 1 plus, that's a sign difference I mentioned, 1 plus the product, tanh phi1 times tanh phi2. And there's an easy simplification we can make with these hyperbolic tangents here. We go back to the definition for phis. So we see here that tanh of phi1 is going to be v1 over c. So I just replace that, v1 over c. Likewise, tanh of phi2 is going to be v2 over c. So that's a new numerator. And the new denominator is just going to be the product of these two, 1 plus the product. Get 1 plus v1 over c times v2 over c. And that's all equal to v3 over c. And if you felt like it, if you don't like these ratios between the velocity and the speed of light, you can multiply both sides by c, and you can rewrite this formula as v3 is equal to the sum of v1 plus v2 in the numerator, and the new denominator becomes 1 plus v1 times v2 over c squared. So here are those two velocity addition formulas that we've derived. What's nice about this one down here especially is that if v1 times v2 is small compared to c squared, and remember c is a pretty large number, then v1 v2 over c squared is very close to 0 because it's some number divided by a very large number. So that's pretty close to 0, which means this denominator is 1 plus a small number, so this is pretty close to 1, which means v3 is pretty well approximated by just plain old v1 plus v2, which is that Galilean formula. That's the naive way of adding velocities. So that's a good approximation when v1 v2 is very small compared to c squared. And lastly, let me give you a little sample calculation just to show you how velocities add when the velocities are very high compared to the speed of light. Now let's go back to A, B, and C. Now let's suppose B relative to A moves at v1 is equal to 1/2 the speed of light. And let's say that C relative to B moves at v2 is equal to, again, 1/2 the speed of light. Now the naive way of adding these two, if we ask how fast is C moving relative to A, is just to sum C over 2 and C over 2 to get C as the answer for v3. But that's not true, and let's take a look at what the actual answer is going to be. So we see that v3 over c is going to be the sum of these two ratios. Now v1 over c and v2 over c are both equal to 1/2, so I just get 1/2 plus 1/2. Then the denominator is going to be 1 plus the product, 1/2 times 1/2. 1/2 plus 1/2 is 1. Then I get 1 plus 1/4, which means I get 1 over 5/4, which means I get 4/5. So that means that v3 is actually 0.8 times the speed of light, not 1 times the speed of light. So hopefully you can see that the way these formulas work is that when you add velocities, the actual answer is a bit less than the naive answer, which is just a sum of the two velocities. And that's because of this correction factor down here in the denominator. And I think that'll finally do it for this video. I think we've accomplished quite a bit in this video, and hope you've learned a bit about split complex numbers and the Lorentz Boost. And if you enjoyed this video, share your thoughts in the comments section, like the video, subscribe to my channel if you like the content, and thank you for watching.